Hello everyone, I'm Lijie Chen from MIT. Today I'm going to present my joint work with Badih, Ravi, and Pasin from Google Research on distributed differential privacy and counting distinct elements. So here's the plan for today's talk. First, I will introduce and motivate the shuffle model of differential privacy. Next, I'll define the problem of study, count distinct element problem, and then state all results for it. Next, I will talk about all results for selection and learning parity in the shuffle model. Then I'll briefly overview all techniques. To prove our lower bounds, we introduce two interesting techniques. The first one is moment matching from the property testing literature. To the best of our knowledge, we are the first to apply them in the study of differential privacy. Second is the dominated protocols. I will define them shortly. And finally, I will conclude with some open problems. So let's get started. First, let me recall the definition of differential privacy. Suppose we have an algorithm M runs on a dataset D consisting of x1 through xn and produces a probabilistic output M of D. And we say two datasets are neighboring if they differ by at most one element. And we say an algorithm M is epsilon differentially private if for all pairs of neighboring datasets D1 and D2 and all possible outputs Z, the probability of M outputs Z is roughly the same under D1 or D2. And why this notion means the algorithm is private? Because intuitively speaking, suppose an attacker A gets the output of MD and wants to learn something about the ith user's XI. We can even assume that the attacker knows everyone else's inputs. Still, the likelihood of XI based on the attacker's information being A and B can be calculated as follows. And since these two data sets, X minus I union A and X minus I union B are neighboring, the attacker cannot distinguish them, and therefore that it cannot learn anything about Xi. And the previous notion is called epsilon pure differential privacy, and then we can relax them to be by allowing a slot tolerance delta. And they're called approximate differential privacy now. A very interesting setting of differential privacy is the distributed setting, while the data set is not held by only one entity, but instead spread over many users. That is, imagine each user holds their own dataset Xi initially. And an algorithm runs the dataset X1 through Xi and produces a probabilistic output M of D. So how do we ensure the privacy of each user? There are three important dimensions one wants to consider in such a setting. The first one is trust. How much should the user trust the curator? The curator is the agent who collects the data and performs an algorithm on it. But the curator may have some motivation which is hidden from the user, so the user may not want to trust it. And second is utility. Of course, we want the algorithm output good enough solutions for the given problem, and that's very important. And second is privacy, and third is privacy. Since we are in the DP region, the extent of privacy can be measured by the epsilon and delta parameters of epsilon delta DP. There are two ways to apply DP in the distributed setting. The first one is the central model, which is the most naive one. So each user holds their own dataset Xi initially, and then they just send their raw data Xi to the single curator. And then they run the algorithm M on the collected dataset. The downside of this model is that after sending your raw data to the curator, you must trust their integrity for the rest of your life. It's not hard to imagine that some years later, the database of the curator is hacked and your data is leaked. In fact, such an information leakage is happening all the time. So that's a price to pay for this trust. And in the local model, instead of sending the raw data, the user first applies a randomizer R on the input and sends the output of the randomizer to the curator. The curator runs the algorithm on the message sent by the users without knowing their original data. So the local model wants to ensure that even the curator cannot learn anything about the user data. So precisely, we can define a local randomizer R to be epsilon locally differentially private if for all pairs of possible inputs A and B and all possible outputs Z, the probability of R outputs Z under A or B are very close. And similarly, we can define the epsilon delta differentially private algorithm as before by allowing some tolerance of delta. So now let's compare these two models for the most basic aggregation problem, in which every user gets a single bit, and the problem is just to estimate the sum. Very basic and simple. So for fair comparison, we want to fix the privacy requirement to be constant epsilon and the inverse polynomial delta. This is the most important setting. So there are two dimensions we want to look at, trust and utility. For the central model, the downside is that you have to completely trust the curator. But the good thing is that you can achieve constant error. For the local model, the fantastic point is that you don't have to trust everyone else, but you pay a lot for that in the utility, and the best error you can get is only square root n. This may not be enough in practice. So a natural question arises. Can we have some model which gets the best of both worlds? Can we get a constant error while putting as little trust as possible in the curator? This is exactly the motivating question for the shuffle model, which answers this question in the affirmative. This model was first studied by ITCS back in 2006 in the name of anonymized communication, and is recently popularized by the need of DP, differential privacy. That is, the shuffle model only requires the user to trust the shuffler, which will be defined shortly, and while it still achieve constant error for the aggregation problem. So very good. So what's shuffler? More precisely, recall that the following are the pipeline of the local model. The shuffle model is an additional layer of a shuffler, which applies a random permutation to all the messages sent by the users, and the curator runs the shuffled version of all the messages without knowing which users sent which messages. In other words, it anonymizes the messages. Formally, we have a local randomizer R and a shuffler S. The transcript with a data set D of x1 to xn is defined as applying a random permutation on all the messages outputted by users using the randomizer R. And we say a protocol is epsilon differentially private if for all pairs of neighboring data D1 and D2 and all possible output Z, the following holds. As you can see, we're just adopting the previous definitions. And similarly, you can define epsilon delta differential privacy. Another important measure for shuffle protocols is the message complexity. A user can send more than one message in the protocol. That is, R on R of X can output more than one items. These messages are treated individually by the shuffler, and after the shuffling, the curator have no ideas which messages come from the same user. And the message complexity is how many messages one user sends in the worst case, which will sometimes be important because you don't want a user to send too much messages. This can cause some overflow in the network, for example. So now we move to talk about our new results. The problem of focus today is the count distinct problem. The input are just n users, each one holds their own data xi, and the goal is to estimate the number of distinct elements among x1 through xn under the constraint of being epsilon delta differentially private. That's epsilon to be a constant and delta to be 1 over polynomial. Since we'll talk about several models, we'll use colors to better differentiate them. We'll use green for the local model, purple for the shuffle model, and red for the central model. And in the central model, it's easy to see that constant error is possible. One can just calculate the answer and then add some Laplacian noise. And our first result is that in the local model, we show that the problem is maximally hard in the local model. And our second result is in the shuffle model. We show that the problem is still maximally hard in the single message worst case shuffle model. And surprisingly, our second result shows that if we relax from the worst case message complexity to the number of messages in expectation, then the problem becomes much easier. First, for the local model, we show that no constant epsilon 1 over n delta local DP protocol can solve distinct with sublinear error. Second, we show that not only for constant epsilon, in fact, for some d equals n by polylog n, for ln d epsilon, the problem is still nearly maximally hard. That is, the error has to be n by polylog n. And surprisingly, we further show that if we further increase the epsilon from ln d to ln n, then the problem suddenly becomes much easier. It can be solved with error square root n. Note that ln d equals ln n minus log n, so it is very close to ln n. Our first result is proved by dominated protocol, and the second result is proved by moment matching. I will talk about them when we get to techniques. For the shuffle model, we first show that for constant epsilon and an inverse quasi-polynomial delta, counter distinct is still nearly maximally hard for the single message shuffle model. And next, we show that if we allow each user send at most half plus =01 messages in expectation instead of worst case, then the problem can be solved by shuffle protocols with square root n error. Hence, there's a big gap between messages in worst case and messages in expectation. To derive our new lower bounds in shuffle model, we prove a new connection between local and single message shuffle model. That is, we show that if a randomizer R is constant epsilon inverse quasi-polynomial delta dp in the single message shuffle model, then it is also ln n minus log ln n epsilon inverse polynomial dp in the local model. Combining this new connection with our local model lower bound, we immediately obtain our new lower bounds in the shuffle model. We also obtain some new lower bounds for other problems in the shuffle model. The selection problem is defined as follows. There are n users. The ith user gets a preference vector xi of d dimension. And for each coordinate j, the score sj is defined as the expectation of xij. And the goal is to find a j star such that sj star is close to the maximum sj. And the learning parity problem is also defined as follows. Still there are n users, and the ith user gets a vector si and a bit bi. And the promise is that there exists a hidden x such that the inner product between si and x equals bi over 2. And the goal is to find the hidden x. We first show that constant epsilon 1 over n delta dp shuffle protocol with at most k messages from each user cannot solve selection if n is at most d by k. And similarly, we show such shuffle protocol cannot solve learning parity if n is at most 2 to the d by k plus 1. Our results are similar to the recent work by Chill and Allman. They study a relaxed version of shuffle model termed robust shuffle model, in which protocols need to additionally satisfy the robust condition, which, roughly speaking, requires the protocol still be private, even if a small constant fraction of users dropped out. This is a very desirable property in the practice because you cannot assume everyone is honest, and some users may be malicious. And they prove that constant epsilon 1 delta robust shuffle protocol with unbounded messages cannot solve selection if n is at most root d, and cannot solve learning parity if n is at most 2 to the d by n, d by 2. The remarkable fact about their results is that they apply to the unbounded message case, where all results do not. On the other side, all results apply to even non-robust shuffle protocols, and also give lower bounds one case at most, and also give better lower bounds one case at most root d for selection. As a bonus result, we also obtain lower bounds in the two-party model and resolved an open question. We show that there's a function f whose global sensitivity is 1, yet no constant epsilon 1/n delta dp protocol for f in the two-party model can achieve error or n by log n. Since we don't have time to cover the details, check the paper for more on definition and this result. This improved the previous 1 versus root n separation and answered an open question by a previous work. Now let us move to the techniques. Since the proofs are pretty technical and long, I will only show the construction of hard instance, and also try to provide some intuitions on why the lower bound should hold for them. Our first lower bound builds on the moment matching techniques. These techniques are first used to prove lower bound for the estimate the unseen problem, which can be seen as the counter-distinct problem in the query complexity model. That is, we are given access to a list A1 to AN, and the problem is to estimate the number of distinct elements in the list within an additive error epsilon times n, and with probability 99%. And we are in the query complexity model. That is, each time one can adaptively pick one element AI from the list to query. And the variant proved that n by log n queries are required to solve this problem, and also sufficient. Later, Wan and Yang sharpened and simplified their lower bounds, and all proofs are inspired by Wan and Yang's techniques. So the key idea in Wan and Yang paper is the moment matching random variables, let L to be log n and lambda to be L squared. That they construct two random variables U and V such that they have unit expectation, and they also have matching moments up to the log n's. That is, for all integers from 1 to log n, the expectation of e to the j equals the u to the j equals the expectation of b to the j. And third, they are supported on either 0 or 1 to the lambda. The most important point about them is that u is mostly 0, while v is mostly non-zero. That is, u equals 0 with probability at least 90%, while v equals 0 with probability at most 10%. To prove our result, we want to construct two distributions of n inputs data sets, d to the u and d to the v, such that no local DP protocols can distinguish them, yet the number of distinct elements in d to the u and d to the v differ by d by 10. Therefore, combining these two together, we'll have the lower bound. We'll use the signal noise decomposition to prove to prove a lower bound. So the setting here is that there are n users, and each one gets an input from 1 to the d for some d equals n by polylog n. And W is that distribution over 0 and or union with 1 to the lambda. W is either U or V. And the E is a random subset of D, such that E is at most set of E is at most D by 100. So we first construct the signal part. For each I from 1 to the D, from 1 to D, we draw lambda I from W. And then we set Ni to be lambda I exactly. And then we add Ni users with input I. And also the construction of a noise part is as follow. For each I in the set E, we set Ni to be n minus D over the size of E. And then we add Ni users with input I. And the construction of D to the W is just that we draw two data sets, D1 from DW signal and D2 from DW noise, and we output their union. Note that since U and V have unit norm, DU signal has D inputs in expectation. And therefore, D to the U and D to the V has roughly N inputs. And the goal is to show that no local DP protocol can distinguish them. We first talk about the purpose of the signal part. Note that since U is mostly 0, this actually means that a data set from DU signal with high probability has few distinct elements. Well, since V is mostly non-zero, this means that the number of distinct elements in a sample from DV signal will be much higher, will be greater than 0.5 times D. Also, note that merging with DW noise does not make a difference, since DW noise is entirely supported on the small subset E, which has at most D by 100 elements. Therefore, these two together establish the second property we want. So we know D to the U and D to the V differ in the number of distinct elements. Indeed, the previous construction does not work as it is, and we have to apply a so-called Poissonization trick, which is famous in the property testing literature. So what's the Poissonization trick? Well, we first recall the definition of Poisson distribution is defined as follows. There's a parameter lambda, and it's supported on non-negative integers. The most important part is that the mean of a Poisson distribution with parameter lambda is still lambda. And the trick is very simple. In DW signal, instead of setting Ni as lambda I exactly, we draw it from Poisson lambda I. And similarly, we'll do the same for DW noise. We'll draw Ni from Poisson n minus D over size of E. After this trick, we can use the fact that D and U have matched moments up to the log n's to show that DW noise provides enough noise so that no local DP protocol can distinguish D to the U and D to the V. Combining these two together, all lower bounds are proved. Of course, the real proof is pretty complicated, but also very interesting. So if you are interested in the proof, the details of the proof, you are welcome to check out the paper. Finally, let us talk about how do we prove lower bounds via dominated protocols. Recall the definition of local protocol are as follows. And we consider a notion called dominated protocols, where we say a randomizer R is epsilon delta dominated if there exists a distribution D such that for all X and the events E, the probability of Rx belongs to E is at most e to the epsilon times the probability of E happens under D plus delta. So diaminated protocols are a special case of local protocols because you can just set D to be Rx0 for a fixed x0 in X. Then the definition of local protocols just implies the protocols are also dominated. Our most important lemma here is that if R is epsilon delta dp in the K message shuffle model on N users, then R is also epsilon plus K ln N delta dominated. Then we prove that selection is hard for dominated protocols. More precisely, we show that constant epsilon 1 over n delta dominated protocols cannot solve selection if n is at most d ln d over epsilon. And putting the connection together with the lower bound against dominated protocols, we immediately get our lower bounds for selection in the shuffle model. And similarly, we can prove our lower bounds for learning parity. Finally, we conclude with some open problems. The first one is whether we can prove lower bounds for unbounded messages in the shuffle model without robustness constraint. The result by Chill and Allman only worked for a robust model, and all lower bounds do not work for unbounded case. So this is a very interesting question. Also, since our single message shuffle model lower bound only works when delta is inverse quasi-polynomial, it would be interesting to extend that to inverse polynomial as well. Currently, it only works for delta equals inverse quasi-polynomial. We believe the problem is still hard when delta equals 1 over polynomial, but the current technique seems not enough to reach it. And thank you so much for your listening, and Happy New Year.